Don't forget your shovel if you want to go to work. Oh, don't forget your shovel if you want to go to work. Don't forget your shovel if you want to go to work. Or you'll end up where you came from like the rest of us. Digging out to the door.
The site is located on the north campus of the University of Limerick, which is within a few hundred metres of the River Shannon. The River Blackwater also runs alongside the site. Recent developments such as the northern campus and Thomond Village are in close proximity to the site. These developments have only taken place within the last 10 years, as before this it was used as agricultural land. The soil is alluvial due to it being part of the floodplains of the River Shannon, as can be seen from historical maps and also more recent OPW flood maps. Here are some photos of recent flooding which took place in late of 2009. Our site visit took place on Monday the 7th of February. We dug 3 trial pits at various locations on the site. Our trial pit 2, the first 3 to 400 mil consisted of brown topsoil. Then we encountered grey and black clay for the next 300 mil approximately. We encountered the water table at roughly 1.2 metres. The excavation trial pit was carried out by a backhoe. As you can see, the grey soil collapsed in on itself after excavation, so we knew that our soil was inappropriate for use. The clay which we planned to use was encountered in trial pit 3 at a depth of 2.3 metres. This was a greyish purple clay which was extremely tough and cohesive.
When we conducted the sieve test to the sample we had obtained, we discovered that we had not found a clay, but a poorly graded fine sand, which we can see from the graph. The steep curve indicates a narrow range of sizes, therefore it is poorly graded. Also, 56% of the curve falls between 0.06 and 0.2 millimeters, which classifies it as a fine sand. Because of these results, we know instantly that we cannot use this soil, as we require a lot less permeable clay. The tests we carried out for the new clay sample were the shear vein test, moisture content, sieve analysis, Atterberg limits, Proctor test, and California Berm ratio. The shear vein test was conducted in situ using a handheld vein tester. This tested the shear strength of the disturbed soil, which was 4 kilopascals, and the undisturbed soil, which was approximately 19 kilopascals. The first test we conducted in the lab was the moisture content, showing us the content of water in the soil sample as a percentage, which worked out to be 65%. Results of this test showed over 20% of the sample was less than 63 microns, contrasting to the bare 4% of our previous sand sample. The Atterberg limits are used to distinguish between silts and clay. Depending on the water content of the soil, it may appear in 4 states: solid, semi-solid, plastic and liquid. The 3 consistency limits are the shrinkage limit, the liquid limit and the plastic limit. The range of plastic states is given by the difference of the liquid and plastic limits, and this is called the plasticity index. The cone penetration test gives us the graph here of water content plotted against penetration. At 20 mm penetration, we can see from the graph that the liquid limit is 40%. The plastic limit of a soil is the moisture content expressed as a percentage of the weight of the dry soil at the boundary between the plastic and semi-solid states of consistency. It is the moisture content at which a soil will begin to crumble when rolled into a thread of 3 mm diameter. The plastic limit of our clay is 24%. The plasticity chart lets us know whether the sample is a silt or clay. The A line provides this division. Clays are above the A line and silts are below it. Our plastic index is the difference between the liquid and plastic limits, which worked out to be 16%. As you can see from the graph, it is just above the A line. Therefore, this shows this soil is clay. The Proctor test gives us a graph from which we can calculate the optimum moisture content to provide the soil with its maximum density. As we can see from the graph, the maximum dry density is approximately 3.05 megagrams per meter cubed, and the optimum water content is about 18%. The California bearing test determines the resistance of the subgrade to deformation under the load of the berm. At a penetration of 2.5 mm with an applied load of 2.5515 kilonewtons, we calculated the California bearing ratio to be 18.9. At a penetration of 5 mm with an applied load of 3.248 kilonewtons, the CBR is equal to 16.24. The greater value is recorded as this California bearing ratio, which is 18.9.
The site where the berm was to be located must have the organic topsoil removed. An impermeable membrane will be laid over the area which will be below water to prevent seepage. The construction will take place in layers of about 200 mm until the desired height is reached. The topsoil used to surface the outside of the berm so grass can be planted and give the berm a natural look. The slope of the berm will be a ratio of 4:1 to cater for future maintenance of the berm. For example, the comfort factor while mowing the grass. Layering construction sequence allows for more controlled compaction, and each layer will be subjected to increased compaction as the height increases.
If our clay isn't of a low enough permeability, the water will seep through the berm, and this will cause flooding and failure of the berm. As you can see from the image, there is a hydrostatic force acting on the berm due to the water. If the berm isn't strong enough to withstand this, it will fail laterally due to this force, and this will result in flooding and probable collapse of the structure. As you can see from the diagram, it is possible that the berm can fail due to a foundation failure. The foundation below the berm could fail if the bearing capacity of the soil is inadequate to support the weight of the berm, which is approximately 20 kilonewtons per meter cubed. This would cause the structure to sink into the ground, and thus failure of the structure and flooding would occur. It is also possible that the berm could suffer a shear failure if the slope of the berm is too great, which for ours berm is 4:1. This would cause structural failure and most likely flooding. Membrane failure is possible. This may be caused by settlement such as movement in the berm structure. It may also be chewed or pecked by insects or birds. At the joining of the sheets of membrane, failure is possible if the sealant is exposed to the sun and dried out.
Health and safety plan will be put in place once the structure is being built. This ensures a safe place of work for staff and safe operation and maintenance of plant and equipment. Basic things like putting up fencing and warning signs to discourage people from entering the site. It even be shocked if they're not careful. The regular inspection of the berm will also take place to make sure that everything's in working order. Life belts will be located on the site in the event of someone falling into the pond. With regards to treatment of grey water, this process is closely monitored in line with health and safety to ensure water going back into the system is of sufficient quality for use. We'll also have a detention pond flood plan in case of emergency.
Captains of industry won't let him blow. He still smokes a cigar, he drives a brand new car. Still he takes his family on a cruise. He'll never